Hello all and welcome back to this course on digital systems. In the last couple of weeks, we looked at designing Boolean circuits that could implement certain functionalities where the inputs were all single bit inputs, right? So though there were multiple inputs, right, to a block, for example the decoder, multiplexer, each of them happened to be just a single bit input, right? Now in practice, that's very rarely the case. I mean, it does happen, but it's quite rare. Many a time you will be dealing with multi-bit inputs, right? Where the bits are all in some sense together give you some information, right? For example, like an n-bit number, right? If you remember the unsigned number, 2's complement representation and stuff like that, essentially it used to come as a package of the 8 bits, 16 bits, 32 bits and so on, and the information is present in all these n bits. Okay, so now we are going to go ahead and build certain circuits that will use this property of this multi-bit representation, and we will see how the design first of all can get very complex if you just try to deal with the truth table directly, right? And on the other hand, if you use the property of each bit as appropriately and use the available available pattern or the available regularity in the circuit, you will be able to implement a design very, very efficiently. Okay, so in that respect, we will start with the most fundamental operation of a CPU, right? In a microprocessor, the addition operation, addition of two n-bit numbers. Right, addition of two n-bit numbers, right? So what we have is, let's say I'm going to choose 8-bit, A7 to A0. So I have bits A7, A6, A5, A4, A3, A2, A1, A0, right? These 8 bits together form the A. Okay, this is my A and my B is going to be B7 down to B0. Okay, now the B7 down to B0 and A7 down to A0, obviously you have to define what the MSB and what the LSB is. So we are saying bit number 7, right, or the 8th bit, right, is MSB, and the 0th bit is the LSB. Now this could be true even if this were a signed number or unsigned number and so on, right? So we'll look at both the signed and unsigned separately, as you know, through examples and stuff, and then we will look at the implementation of this adder. Okay, so let us say now I have something like this. Okay, A. Okay, so usually when it is 1 bit we just write 1 arrow. If it is multi-bit, we could put this cross line here and indicate the number of bits. Okay, B. Okay, this is my thing, and now I need to get a sum S. Okay, and what I'm trying to do here is to implement an adder. Okay, so we'll come to this. Now first of all we need to determine how many bits this sum could be. Okay, so let us first deal with some examples so that we get a feel for it. Okay, I'm going to do unsigned addition first. Okay, unsigned addition. So let us take an example where both A is, let me say 0, 1, 1, 1, 1, 1, 3, 4, 1, 4, yeah, okay, and my B is 0, 0, 1, 1, 1, 1, 1, 1, okay. So if you look at this number here, we are talking of 2 power, this is 2 power 7 minus 1, okay. It is 2 power 7 minus 1, which means this is 127, okay, and the other one is 64 minus 1, so it is 63. So if you do 127 plus 63, what should you get? You will get right. So I'm doing this here just to explicitly show you, how the carry propagates, because we will be doing exactly the same thing even in the multi-bit addition here, right? So 9, and I have this. Answer should be 190, okay, unsigned number again. And so now let's go ahead and see if we can do this addition using 0, 0, 1, 1, 1, 1, 1, 1, okay. So first of all, you noticed that in the decimal case, when we did this addition, we added two numbers, we got a carry that went on to the next bit, the next digit, and of course the remaining result was just put below. We are going to do exactly the same thing, except that we are going to do this addition in base 2 number system. That means that only numbers allowed are 0 and 1, and anything beyond that will become a carry, okay. So let us look at this example. I am going to represent the sum, okay. So 1 plus 1 is 2, okay. Remember, now we are, before that let me clarify, this plus here that we are talking about is the addition operation, is not an OR operation, okay. So just to clarify, it is possible for us to define something known as a bitwise OR operation, okay. I could have A or B, where you simply take A0, B0, send it through an OR gate, and you get the answer Y0, right. Similarly, you do this for any arbitrary A bit, AK, BK, and you will get the answer YK, okay. So if you have an n bit number, A and B being n bit numbers, you have n OR gates, 2 input OR gates, you will get the answer. Now that is what you call here. Sometimes that may be written like this, A plus B, but it will be explicitly mentioned that that is the bitwise OR operation. Now we are talking about the same plus symbol representing the addition operation, okay. The context will of course make it clear, but even otherwise it will be explicitly mentioned where there could be a potential confusion. So anyway, so you start as usual from the LSB, right? You're going to start from the LSB A0, and you do 1 plus 1, it is 2, so it becomes 1, 0. So I'm going to write 0 here, and the carry is going to go up as the next bit, that it has to be added with the next bit, okay. Now I have 1 plus 1 plus 1, 3 ones. So the answer is 3, and therefore you will have another carry of 1, and the sum coming down here as 1, okay. Maybe let me put this in blue, 1, 0, right. Now again I am going to do the same thing, 1, 1, 1, so I get 1 here, and the carry will be 1 here. That same thing is actually going to continue, so I am going to just put it until where it is supposed to happen, okay. So everywhere you see there is addition of 3 ones, answer will be 1, 1, so you take the carry and keep propagating it like that. So finally we have, when you are at let me just maybe move this a little down so that I can represent the bit position also nicely in this case. Yeah, okay. So here I am talking of bit position 0, 1, 2, 3, 4, 5, 6, 7, and obviously this is A, this is B. Okay. So now I have at bit position 6, 1 plus 1, which again is going to be 0, and eventually you have a carry of 1 to the next stage, and then the 1 plus 0 is going to give you 1 as the answer. 0. I mean 1 as the answer, not 0. Okay. So therefore it's very evident that we were able to do the binary addition in a manner very similar to what we are used to in the decimal system, right? And in this case, it so happens that the answer is representable in just 8 bits. Okay, you didn't have to go to an extra bit, right? So, so first of all, we can check our answer. Is this equal to 190? It is 2 power 7, okay? 2 power 7 is 128, okay, plus 64, this is 32, 16, 8, 4 plus 2. So you can now check 16 plus 8, 24, 24 plus 6 is 30, and 128 plus 32 is 160. So this is equal to 190. Right. So this makes complete sense, and the two answers are indeed they indeed match. Okay. Now let us now push the limit of this and see if the answer is always representable as an 8-bit number. Okay. So let us look at the case. What is the maximum value of A and B? Right, because that's the largest addition that we need to do. If you can take care of this case, you can actually take care of any other case that you want, right? So this is again 7, 6, 5, 4, 3, 2, 1, 0, right? I'll leave some space for the carry B. So what's the largest number? Obviously, it's just everything being a 1, right, which is 255, right? And okay, this is what you have, right? And let's go ahead and do the addition in exactly the same manner that we did earlier. 1 plus 1, 0, you will get a carry of 1. Now everything is 1, therefore you have to essentially keep carrying a 1 over like this, right, including this 7th bit, right, or the bit position 7 or the 8th bit actually, right, and all this has to be 1, 1, 1, 1, 1, 1, 1, right. So essentially we have this as the answer, just that in bit position number 7, instead of the earlier case where we just did 1 plus 0 or something, we now need to do 1 plus 1 plus 1. So the answer will be 1, 1, and therefore you will have this as the answer. Okay. And what is 255 plus 255, by the way? So if you look at this, 255 plus 255, right, it is how much? 10, 11 and 510. Answer is going to be 510. Okay. So now the question is, how many bits do I need to represent 510? Well, clearly it is just too short of 512, and therefore you need that 9th bit as well. You need the 2 power 8, 256. Okay. So therefore you will see that bit position 8 is also needed, though in this case, because they are unsigned numbers, we are just extending zeros, Okay, if you remember this from the initial weeks, unsigned numbers you extend by just adding zeros in the beginning, right, beyond the MSB, right. For signed numbers, that's a different story altogether, and therefore your sum is going to be S8 to S0, okay, and therefore this is 9 bits. You need the sum which is S8 to S0, right, or I will just say 9 bits here. Okay. Now let's actually, before we proceed with the implementation of this circuit, let us also look at some unsigned number, signed number calculations. Okay, I am going to now say A is 8-bit 2's complement. Number, okay. B is also the same, right. So therefore, remember the range that A and B can each sort of represent will be quite different. Okay, so we can again start with 2 examples. Let's take A equal to 0. Both will start with both positive numbers, 0, 1, 1, 0, 1, 1, 0. Or maybe I will just do this with 4-bit numbers, okay, so that it's just easier for us to do, because the same thing will carry over to 8-bit as well. Okay, this is 4 this thing, so this is basically A3 to A0, okay, B3 to B0, right. Now what do I have? Let's say A is equal to 0, 1, 1, 0. I want both to be positive numbers in this case, 0, 1, 1, 1. Okay, so what is this number in 2's complement representation? It is 6, and this is 7, right, and 6 plus 7 is going to be 13. Now if you want to represent 13, then you obviously need an extra bit in 2's complement representation, because I need the answer to be plus 13 here, by the way. Okay, let's be very careful about this. It is plus 13, and therefore I need my answer. This thing should actually be 0. So 2 power 4, 2 power 3, right. Okay, this is minus 2 power 4, 2 power 3, 2 power 2, 12, 0, 1. This should be the actual answer that we get eventually, right. So let us look at how we go ahead and do this. Okay, 0, 1, 1, 0, 0, 1, 1, 1. Okay, again I am doing a plus here, right. So 0 plus 1 is 1. I am not going to worry about the color coding they carry now. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 0, 1, 1, right. And the answer is 1101, but remember, it is, I have to sign extend this. If I say the answer of A plus B is 1101 and you are expecting a 2's complement output, this is incorrect, because this is actually equal to minus 3, remember. Okay, so you have to sign extend and say 01101 is the answer. Okay, this is the only correct representation of plus 13 in 2's complement representation with minimum bits. Okay, so therefore be careful about this part. Okay, so here it is quite obvious, we already needed that 5th bit, right. 0, 0, 1, 2, 3 and A4 and B4 and S4 was already needed. Okay, let's now consider the case where I have a negative number 1 0 0 and B equal to 0 1 1 1. Let's see what this is. Okay, this is actually equal to -8 and this is equal to +7. And if I add these two, I should get -1 as the answer, which means this should be 1 1 1 1 and 1. Right? Of course, you can extend this to as many bits as you want. Right? So let us look at that. 1 0 0 0 0 1 1 1. Okay, I'm going to add. So we'll do this a little carefully. 0 plus 1 1, 0 plus 1 1, 0 plus 1 1, right? And 1 plus 0 is, obviously it is going to be equal to 1. Okay. Now this again is only 4 bits. So how do we get that 5th bit? Remember, you have to sign extend. So I will sign extend now in a different color. I can extend this to as many bits as I want on for both guys because they are 2's complement numbers, and then I do the addition, and you can do how many ever bits you want now. You will get the answer. Remember, -1 is just all ones irrespective of how many bits you take in 2's complement representation. So therefore, you pull this sign extend A and B to how many ever bits you want, and the answer should still be consistent. That is the whole point of this sign extension logic that we are talking about, right? So effectively, this is not, so if you look at this, we get, just this. So let us also do A equal to -8 and B equal to, let's say, -3. Okay. So this should be what? Answer should be -11 effectively. So let us try this and see. So -8 again is 1 0 0 2 power 0 1 2 3. -3 is actually -8 plus 5. So 1 1 0 1. Okay, and we want the answer to be -11. Okay, so this is -16 plus 5. Right? So 0 1 0 1. This should be the answer. Okay, this is the expected answer. Okay, so let's see if we get that. 1 0 0 0 1 1 0 1 0 plus 1. Okay, bit position 0 1 2 3 4 5, and I can actually write how many ever I want here. Okay, plus. So 0 0 plus, so bit position 0 is 0 plus 1, so you get 1. Bit position 1 0 plus 0 is 0 1 0, and then I am going to carry over a 1 here. So let me just move that. I am going to carry over a 1 here. Okay, so this is bit position 0 1 2 3 4 5 dot dot dot. Now you just see what happens. Okay, I'll also show you in this case, if you don't sign extend correctly, what will happen, right? So this A and B are 2's complement numbers. Now if I incorrectly sign extend like this, okay, what am I going to get? So okay, in this case it just turns out to be this. Okay, I have to sign extend this first of all, right? So sign extension I'll do with magenta like this, 1 1. Okay, now you see what happens. On bit position 4, I am adding 1 1 1. Okay, so I will get the answer as 1 here and a carry 1. Okay, again I am doing 1 1 1. It doesn't matter, right? Same thing will happen. 1 carry 1. So you can go to as many bits as you want. Okay, and it will still give you this 1 1 1 1 1 1, right? So if you look at this, this happens to be the sign bit of the sum. Okay, that's the MSB of the sum in minimum number of bits needed to represent that answer. So you get 10101. Okay, this is the answer that we expected to see. But of course, if you sign extend this, you should get 1011111, then 10101, right? So that is exactly what is happening. Even if you sign extend A and B to as many bits as you want, you will still get the right answer in this form of addition, right? So the key takeaway here, right, is that irrespective of whether it's a unsigned number or a 2's complement number or whatever it is, the addition circuit or the addition logic is exactly the same. You just don't care about it, right? You just add numbers and you just continue doing it, right? The only thing you must be careful about is the sign extension, if at all, that you need to do properly, right?